welcome back.
We are going to continue to study Newton's law. Um, we have said on the previous video that Newton's law are only valid when the observer is an inertial observer. What is basically an inertial observer? An inertial observer is the observer that is moving with constant velocity. What it means that he's moving with constant velocity, respect to whom? So approximately this can be a good definition, but it's not a good definition like this. An inertial observer is the observer that is really moving at constant velocity, yes, but the inertial observer, it will observe a rectilinear line when nothing is acting on an object. So the initial observer will place his axis x and y, and he will see a rectilinear line of an object that is moving and nothing is interacting. The magnitude of the object that he is observing is constant, and the direction of V is constant. When this is happening, when nothing is acting on the object and the inertial observer is observing this rectilinear line, we say that he is really indeed an inertial observer. When something is happening, well, the inertial observer will not observe a rectilinear line and will say, now my vector velocity is changing. Maybe magnitude, for sure in direction. And now he will observe not a rectilinear line. So this inertial observer will say that something happened to the girl, and what is happening is something is acting on the girl. And he will say that there is a force acting on the girl, and the force is making the vector velocity to change. The V initial will be like this, the V final will be like this. So it will be a change in the vector velocity, and the force is proportional. The force acting during the time is proportional to the change in the vector velocity. So the force, the vector force acting during the time is m by delta v. And this is, of course, F equal ma. This is the same that say F equal ma. So we have inertial observers, inertial system of reference. The Earth is not an inertial system of reference because the Earth is rotating, and the vector velocities of the observer will be changing all the time. So he's subject to some kind of acceleration that makes him not to be an inertial observer. We will consider that the Earth more or less is an inertial system of reference because we will think that for some interval of time, the inertial observer that is on the surface of the Earth is moving almost in a rectilinear line. Let's go to see more features of this chapter.
When we talk about
Forces, we involve the mass. The mass of an object is an scalar, is a number, is a positive number. But what is mass? One definition may be that mass is the amount of matter, but it's not a very complete definition. It doesn't say the essence of what is mass. The other maybe definition could be that mass is the measure of the inertia. What it means that is the measure of the resistance to change the vector velocity. So you change the velocity acting with a force that is acting. If the mass is a very massive object, the force will make a small change in the velocity. So mass is the resistance to the change in the vector velocity. For example, a truck have a big inertia. Why? Because it has a big mass that when he's moving at certain velocity, even a small velocity, uh, to stop them need a big force. While um, while if there is a bicycle is moving at the same velocity, at the same vector velocity, same direction, to stop the bicycle will be much more easier. You will apply small forces in the opposite direction at the vector velocity to stop the bicycle. It will be easier because the mass, even if the vector velocity are the same one, same magnitude and same direction, the mass is smaller. So mass is a measure of the inertia, is a measure of the resistance to change the vector velocity. Now we study the concept of weight. Weight is related with mass. Every object has a mass, is inherited. You cannot change the mass of the object. Is and the Earth create a gravitational field that pull down the mass and create acceleration of the mass. So the mass is here, this is the mass, this is the Earth, and the Earth create an acceleration here. What is the weight? The weight is a force, is the mass by the acceleration. But the acceleration in this case is always the same. It's always 10 meters per second square going down. Why? Because the gravitational field, in some way, it doesn't make any difference if the acceleration that produces the Earth, it doesn't make any difference between the color of the object, between the mass of the object, between the shape of the object. It will accelerate any object that you put here. Even if it's a massive object, it will accelerate with the same acceleration, 10 meters per second square, going downwards. So weight is mass by acceleration. Then is a force. So the force is m by a. And the acceleration is the force per unit of mass. This means that when you think of acceleration, 10 meters per second square, you may think newtons per kilogram. So 10 meters per second square will be the same at 10 newtons per kilogram. Let's go to write this. 10 meters per second square is equal at 10 newtons per kilogram. So it means that every kilogram is being acting a force of 10 newtons. Okay, so imagine that I have an object of mass 2 kilograms and I apply a force of 10 newtons. What is his acceleration? His acceleration will follow the direction of the force. So A will be F divided by M. M is an scalar, is a number. So in this case, if the force is 10 newton going to the right, let's say this force produces this acceleration. And the acceleration will be the force divided by the mass. The force is 10I divided by the mass, so the acceleration will be 5I. What is now if the force is now a different force in a different direction? If this is the force now, 10 cosine of 45I plus 10 sine of 45J is this force. Is this force. What this force going in the 45 degree xy, x and y, is going in the 45 degree direction, a positive 45. And what is his acceleration? The acceleration is the force per unit of mass. The force is 10 cosine of 45I plus 10 sine of 45J. And the mass is 2, 2 and 2. So the acceleration will be 2 cosine of 45I plus 2 sine of 45J. So in this case, the magnitude of the force is 10. You can see, you can recheck that the magnitude of this force is 10. Of course, this square plus this square root will be 2, will be 10. And you can also check that the magnitude of the acceleration here
is also
should be 5. So let me erase here. 10 divided by 2 is 5 cosine 5I plus 5J. So the magnitude is 5 meters per second squared, and the force is 10 newtons, and this force in this direction produces this acceleration. And the magnitude of the acceleration you can also check is also 5. But the acceleration will be 5 cosine of 45 plus 5, sorry, that I made a mistake here. It will be 5 cosine plus 5 sine of 45J. So in both cases, you produce the same acceleration because it's the same force and the same mass. But you produce the same amount of acceleration, but it's in a different direction. This acceleration that have the magnitude 5 is in a different direction than this acceleration that have the magnitude 5 also, and is 5I. So forces produce acceleration. Let's go. M for
so the summary
is that what is the difference between weight and mass? Mass is the amount of matter that the object have is something constant. It doesn't change unless you break the object into pieces. If you take it to the moon, the mass will be the same that in the earth. But what is different is the weight. The weight is the force that the gravitational field pull the object down. So this force of attraction is the weight. And the relation between the weight, the force equal mass by acceleration. This is the acceleration created by the Earth. This is the mass of the object. And this is the force, the weight. The weight is a force, is a vector. So the mass is measured in kilograms, while the weight is measured in newtons. Capital M
mass are
always positive. It doesn't exist in negative masses. Masses are always positive. So the weight goes in the direction of G. So if G goes downwards, the weight goes downward. If G go upward, the weight goes upward. The weight or the force will follow the acceleration. So the acceleration is always, as I said, measured in meters per second square, you know that. And it can be seen, it can be also measured in newtons per kilogram. So one of the things that maybe is something striking, why object of a different mass doesn't have different acceleration when they fall down. In 500 years ago, Galileo proved that if you try to depreciate friction forces, if you make an experiment where there is no friction forces and there is only gravitational force, the weight pulling down, and you choose a small mass m, the small mass m will receive the force that is mg. The big mass m, imagine a mass composed of 9 mass little m, 9 little m. So the weight will be bigger. The weight will be 9 times the mass m, 9 times m, little m by g. The weight will be m by g, and in this case the mass is 9 times m by g. By the acceleration g is the same
the capital M
for the little m. It will be the same acceleration. Both of them will fall down with the same acceleration. G, 9.8, 10 meters per second squared, 9.8, let's say. It doesn't depend on the mass. The acceleration that is pulling the object, it doesn't make any discrimination about how massive are the object. While the weight, yes, the weight, the force is smaller here in this case of a little m, and here is much more bigger because the force is mass by the acceleration. So the g is always the same and it doesn't depend on the mass. So imagine that my mass is 100 kilograms. So my weight should be 100 multiplied by the acceleration that is pulling me down. And the acceleration that is pulling me down is about 10 meters per second square. So my weight, the force that the earth is attracting me to the floor, is attracting me down, is 1,000 newtons. So this means that every kilogram of my body is being accelerated by 10 meters per second square or 10 newtons per kilogram. So every kilogram of my body receives a force of 10 newtons every kilogram. So because my body is 100 kilograms, the force that I will receive will be 1,000 newtons. Now, if I move to the moon, my mass will be the same. It will be still 100 kilograms. It's the amount of mass that I have. But the acceleration that the moon produces is smaller. So the weight, the pulling force, the force that pull me to down in the moon will be smaller because the acceleration is about 3 newtons per kilogram or 3 meters per second square. So the weight in the moon will be around 300 newtons. So my mass is the same, the weight is different because the g is different. So your weight depends where you are, but your mass is always constant.
So, as a summary, we will
Will say that all objects that are in the presence of the gravitational field of the Earth will the gravitational field will induce an acceleration of every object of 9.8 meters per second square or 9.8 newtons per kilograms. And this acceleration does not depend on the mass, does not depend on the matter, does not depend how massive is the object. It will induce the same acceleration to every object. Light objects, heavy objects, massive objects will fall with the same acceleration. But what will be different is the force that is acting on the light object or the force that is acting on the massive object. But the acceleration of both of them will fall with the same acceleration.
this experiment
Experiment was done on the moon to check what we said. What we said is that every object will have the same acceleration. So the light object, little m, will have an acceleration g on the moon, let's say 3 newtons per kilogram or 3 meters per second square. The massive object, let's say a very massive object, will have exactly the same acceleration of 3 meters per second square. So if you launch the two bodies at the same height, they will arrive to the floor at the same instant because they have the same acceleration. they will, when the object is here, the massive object is here, the light object will be here. So they will make the same change in velocity because the acceleration is the same. And as you know, the acceleration is the change in the velocity per unit of time. Or in one direction, in the y direction, ay is delta v divided by delta t. But in this case, ay is g. G going down minus g equal delta Vy divided by delta t. And this is the equation that happens to be. So because the both objects, even the light one and the massive one, have the same acceleration, they will change its velocity and they will go downwards simultaneously with the same velocity always. So they will arrive at the same instant of time to the floor of the moon. This is only in the case that there is no friction. If there is friction, the shape of the object will be affect the motion, will create acceleration, different acceleration, and what I have said will not be true.
Now, this is the
Space station. In the space station, there are people living and observing the Earth from a satellite. It's like a satellite space station. I think that there are like 10, 12 people living on the space station. And the space station is rotating around the Earth. And you may think that when he's rotating, the astronauts that are in the space station, they are not subject to weight. And it's not true. You will see them um, moving inside the space station like they don't have any weight. But is true that they don't have any weight? No. They have a weight, but the apparent weight will be zero. And the reason why this is happening is because of the following thing. Imagine that you are in an elevator and the elevator is going downwards with the acceleration g. So you are accelerated downwards with the acceleration g. So imagine that you take your wallet and you put the wallet here, and the wallet will follow with acceleration g. So both of them will be following downwards with acceleration g. And
the force of
gravity will pull you if your mass is capital M and this is little m. The mass, the force will be mg, will be a little force, while here the force will be mg. But because both of you, the packet or the wallet or whatever you throw, both of you are falling downwards at the same acceleration, you will always see the package in front of you. And you will look, it seems to me,
it will seem
apparently it will seem for the guy that the wallet is on the air, is not subject to anything. It will look for this point of reference, it will look the object suspended in the air because they are both falling at the same time with the same acceleration. He will look the object always in front of him and he will think, this guy will think of the object that there is no weight. There is no weight because he will think his relative acceleration will be zero. But in this is not true. There is a weight here acting on the object, and there is weight here acting on the wallet or the package that you launch. it seems to you, to the guy that is falling with the package, that nothing is attracting them downwards. But in this, the weight exists. The weight is mg. So in the space station, what is happening is that the space station is going around the Earth. This is the Earth. This is the space station. The space station have an acceleration going in this direction. This is like a circular motion. And you are going also with the same acceleration in this direction. So it looks like nothing is, that you have no weight, but the apparent weight is zero, but you have the weight of the force that the gravitational Earth, that the Earth is pulling you down. Let's go now. So now we go directly to the practice. How we will use Newton law. Newton law, we will use it following 5 steps. On the first step, we write the equation in vector forms. What it means, we write the equation of vector forms. We write F, the sum of the forces, and we write in vectors, equal the mass by the vector acceleration. In the second step, it's important to write the equation because it will remind us that we have to sum all the forces, and the sum of all the forces is mass by acceleration. So the acceleration is produced not for one single force, it's produced by the sum of all the forces. The sum of all the forces produce acceleration. Once that we will do, we will write this, we go to step 2. On step 2, we isolate the object and we identify and draw all the forces that are acting on the object. This is a very important step, to isolate the object, to see what forces are acting on the object, to make the sum here, to make the sum, and once that we made the sum, we make the sums equal mass by acceleration, the mass of the object by the acceleration of the object. So in step 3, we write again Newton's law with the forces of the problem. Once that we isolate the object, we see what forces are acting, and we rewrite again Newton's law, but now we know what are these forces. We know what are the sum of the forces because we know which one are acting. On the step 4, we choose a system of coordinate that will say in what direction is the positive direction and what direction is the negative direction. And once that we choose the positive direction and the negative direction, we again rewrite the second law in this direction and we solve the equation. For example, let's go to practice as a few examples. Let's say that this is the mass. The mass, let's say that is at the floor, and the change in velocity of this mass is 0. So if the change in velocity of this mass is 0, well, A is 0. Of course, A is 0. So what Newton say? On this object, we isolate the object. We do the step 2. The step 2 is isolate the object and we see what are the forces acting on the object. What forces do I see acting on the object? I see the weight going down. The weight going down. And I see that there is a force that the floor is doing on the object, all the forces are on the object, and I call this force the normal force. So I will write my equation, the normal force plus the weight, the sum of the two forces should be equal the mass by the acceleration. But because I observe that the acceleration, the change in velocity is 0, I will say that the normal force plus the weight equals 0. That what will say? It will say that the normal force is the weight, but with a minus sign. So if the normal force is going in this direction, the weight have to go downwards, normal force and weight, in a way that the normal force plus the weight is zero. And because you know how to sum vectors, you know what I have said. So the equation, the step 3, is solved by writing n plus mg equal ma. Now you will choose a direction. What is the direction that you would choose? Let's say that you choose the standard direction y positive going up. So the normal force is positive and the mg is negative going downwards. mg, mg, and n. So now you will write a scalar equation. The normal for the n is positive, so I will write plus n. The mg is negative, I will write minus mg. And the sum is mass by the acceleration. But the acceleration is zero, so the mass by the acceleration in this case will be zero. So as a conclusion, I have that the normal force, the value of the normal force is mg. mg is the force that is going upward and sustain the mass because there are another force going downwards that is mg. N, the force N with the value plus mg is the force that produces zero acceleration because I have the sum of the forces, one going up, mg going up, plus mg going down, the sum of all the forces is zero. So the sum of all the forces is zero, so the acceleration should be zero in this case. So following these steps will help you make mistakes. Let's go to do, for example, this problem. We want to find the tension on the cable in an elevator in different cases. So we will go to the we will follow these steps. Step 1, write second Newton's equation in vector form. The sum of all the forces equal ma. Okay, I write the equation. The second step, isolate the object and identify and draw forces acting on the object. What is the object? The object is the elevator. The elevator has a mass m, and it say isolate the object. Okay, this is the elevator. This is the elevator. Identify the forces that are acting on the object. It's very important the word on the object. On the object, there is a force pulling him up that I will call the tension. And on the object, there is a force pulling down that I will call the weight, mg. Third step, okay, so I have identified for the mass m of the elevator that what are the forces that are acting on the object. Write the Newton's equation in vector form. Okay, the vector t plus the vector mg should be ma. From here, I know that the vector t should be m by a minus g. And now the step 4. The step 4 is say, rewrite the equation. Now we have to choose a system of coordinates. So the acceleration is going up. So let's go to choose positive acceleration by saying that y is going in the positive direction. So this is the positive direction, in the same direction that the acceleration. So the tension is positive and the weight is negative. So I will write this equation 3, using the fact that the tension is positive, the weight is negative, the acceleration is positive acceleration. So the tension on the cable will be mg plus ma. Let's go to do a problem. Let's say that the acceleration of the elevator is 10 meters per second square going up. So I would choose it up, positive. Let's say that the mass of the elevator is 1,000 kilograms. Am I asking if the acceleration is moving a equal 10 meters per second square up, and there is a force T pulling up the object, and there is another force pulling down the object, that is the weight, what will be the tension? So you will say, okay, how many forces are going up? You would choose the positive direction like this, the same. If you want, you can choose always the positive direction as the direction where the acceleration is taking place. So you will say, what are the forces that are going up? T. What are the forces that are going down? mg minus equal mass by acceleration, but this acceleration is going up. So it's m by a. So the T will be m by a plus m by g. Now it's not a vector equation. Now it's an scalar equation, because I have the magnitude of T is going up positive, the mg is going downwards negative. So the T, the tension that is capable to make 1,000 kilograms to move at 10 meters per second square up, is this force, 1,000 by 10 meters per second square. So the tension that will produce the elevator to move up at 10 meters per second square will be 10,000 plus 10,000 will be 20,000 newtons of force can produce an acceleration of 10 meters per second square. We can check. So I have the elevator here. I have now 20,000 going down. I have now 10,000 going downward. G, M by G is 1,000 by 10 G. So how many forces do I have? So the sum of all the forces is 10,000 going up. And my Newton's equation say that the sum of all the forces is the mass by the acceleration. Okay, let's go to check. The sum of all the forces is 10,000. The mass is 1,000. And the acceleration is 10 meters per second square going up by 10. Ooh, 1,000 by 10 is 10,000. It's true. It's true. Okay, let's
go to analyze this.
Same situation when the elevator is here. The acceleration is going downwards, A. Let's say that A is 5 meters per second square going downwards. There is a tension here, T, and there is the weight here, mg. mg, and imagine m equal 1,000 kilograms. So they ask me, what is the tension? So what I will do, I will say the sum of all the forces equal the mass by the acceleration. This is my Newton's law. So I will identify the forces. I already identified the forces. There is a weight going down, there is a tension going up, and the object is accelerating downwards. How I will write my equation? Well, if I write my equation in vector form, I will write T plus the weight mg, the vector mg equal ma. Now I need to place the equation in an scalar algebraic numerical way where I can find the tension T. Okay, how I will do? First of all, I will choose what is the positive direction. So I will choose the positive direction, this direction, the direction of A. And I will say the forces that are going up is the tension T, that is minus T now, plus mg equal m by positive A, because I have chosen the positive direction going downwards. So mg is positive and T is negative, and this is m by a positive thing. So now the tension T will be different. The tension T should be smaller now than before. So the tension T will be mg minus ma. So the tension T will be 1000 by 10 minus 1000 the mass by 5. So it will be 10,000 minus 5,000. It will be 5,000 newtons, the tension in this case going down. So going up, the tension was, well, I think that I changed the magnitude of the acceleration. It's a pity that I did that, but you can get an idea. What happened now in the case where the elevator is moving with constant velocity, let's say 10 meters per second. So there is a tension of the cable, there is the weight going down, mg, and the velocity is constant. If the velocity is constant, the change in the velocity is zero. 10 minus 10 is zero. The acceleration is zero. So the equation that I will place is that let's say that I choose going down the positive direction. So I will write mg going down minus t will go up, minus t going up. I choose minus t equal m by a equals 0. So t will be mg. Let's say that I don't agree to choose the positive direction going down. I might want to place the equation. This is the object is moving with v equals constant, going downwards with velocity 10 meters per second, and with acceleration, of course, 0. And let's say that you say, no, let me choose the positive direction going up. Okay, if you choose the positive direction going up, the weight will be negative. So the equation that you will place is T minus mg equal ma, 0, because the acceleration, so T will be mg. Okay, let's go to do another case just to practice. Let's say that the acceleration is going downwards. I'm going to make it, let's say 5 meters per second squared. So if the tension T is the weight going down, mg. So the total force producing acceleration going downwards of 5 meters per second squared. So this means that there are more forces going downwards than going up. Otherwise, you cannot accelerate going downwards. So how I would choose? Let's say that I choose the positive direction in this direction. This is my positive direction. So mg is positive and T is negative, and the sum of all the forces is this, and the sum is the mass by the acceleration. So in this case, the tension will be mg minus ma if you are going downwards. Let's say that you are not happy with this and you want to choose to do the same problem, the tension T, the acceleration going downwards, 5 meters per second square, and the mg going downwards, and the tension T. And let's say that now you want to choose the positive direction in this direction. So you would say the T is positive, the mg is negative, and this produces an acceleration m by a. So the tension will be mg plus m a. You see, this equation is different than this equation. Oh, why? Why? Because in this case, in the second case, this acceleration is not 5. The acceleration, if I choose the positive direction going upward, the tension is positive and the A is negative. So this will produce here a negative acceleration. And now the tension will be mg minus ma, and will be the same tension that is here. So try to see how to play with this equation, and you will for sure you will catch it.
In this case, of
Or
course,
we can calculate the tension. So there is an object moving downwards with 5 meters per second square. I want to find the tension. The tension will be mg 1000 by g10 minus ma 1000 by 5. So the tension will be 10,000 minus 5,000. So the tension will be 5,000 newtons. And this tension is going upward. So the problem is that you have uh, you have you have the weight that is mg, that is 1000 by 10. You have 10,000 going downwards. Perfect. You have 5,000 going upward. That is the tension. The total amount of force is 5,000 going downwards, and 5,000, a force of 5,000 on an object, a force of 5,000 newtons on an object of 1,000 kilograms produce force, the sum of all the forces equal the mass by the acceleration. The sum of all the forces is 5,000 going downwards. The mass is 1,000 and the acceleration is a. It produces 5,000 divided by 1,000, or 5 meters per second square. So it is correct what I have done. To review this idea again,
we have that
our general equation will be mg plus ma. So if a equals 0, v is constant, t will be mg. If a is positive, going up, the tension will be bigger than the mg, because it's the only possibility that t will be bigger than mg to produce a positive acceleration going up. If a is negative, the acceleration is going downwards. We consider downwards negative, so the tension will be smaller than mg. If A is equal G, the tension will be mg plus mg. While if A is equal minus G, if the acceleration going downwards of the elevator is exactly minus G, the tension will be 0. Think about this case. So A is going downwards with magnitude G, and this is a free fall in this case.
now
Read these things carefully. See what is being done. Stop the video.
this part we are going
To do the same thing that we have done with the elevator, but now the object will not be the elevator. The object will be the guy. We will see the forces on the guy. And we'll imagine that the floor is acting like a scale that will measure the weight. So the normal force that is acting on the guy will be what the scale will be measuring. So we will do the experiment to put the guy into an elevator. The elevator will go up at certain acceleration, and what we pretend to know is what will be the measure of the scale, what will be his apparent weight.
Do the same thing.
Stop the video, see what I wrote, and solve the problem. Elevator, case 1, elevator accelerating upward. So you solve the problem. So let's go to do it. Imagine that I have the guy. So I'm going to very fast. Imagine that I have the guy, the elevator is going up. So the guy is going up with acceleration A. The floor is going up with acceleration A. So the floor is pulling the object. So we will see the objects, the forces acting on the object. The object is the guy. So there are several forces acting on the object. Only two forces acting on the object. Forget about the tension that pulled the elevator. This is not what is acting on this guy. The forces that are acting on the guy is the weight. The weight is acting on the guy, is pulling the guy downwards, and the other force is the force that the floor is doing on the guy, that we call the normal force. As you see, if I have acceleration in this direction, I need to have a total force, a net force in this direction. This means that the normal force have to be bigger than the weight. Otherwise, you cannot produce acceleration in this direction. So we go to our step. Step 1, write the second Newton equation in vector form. N plus W equal ma. Step 2, well, choose a positive direction. I will choose the positive direction going up and write the equations. So the normal force N will go up, and the weight will go downward. N minus mg equal m by a. A is going up also, so this A is positive. So the normal that he will measure, the scale will measure a normal force that will be bigger than the weight, and it will be bigger than the weight in the amount ma. So we can do calculations. A person of mass 100 kilograms is an elevator that is moving upward at plus 5 meters per second. What will be his apparent weight? With apparent weight will be the normal. And what will be the normal? The normal we already calculated. mg plus ma. mg 100 plus 10 multiplied by 10. ma 100 by 5. So his apparent weight will be 1,500 newtons. So he increased his apparent weight. No, his weight is still 1,000, but his apparent weight, the weight that the floor is pulling him up, will be 1,500 newtons. So this is the apparent weight of the normal force. You can
Again, stop the video.
see what I wrote and see option 1, see option 2. Let's go to the problem when he's going down. When he's going down, the weight, the weight will be always the same. His mass by the gravitational going downward by 10. But his apparent weight in this case will be lower. The scale will measure a lower apparent weight.
You do it.
You see what I did. You see what I did, and you do it, and now instead of 1,500 newtons, you will find that the apparent weight, the normal force, will be 500 newtons. Option 2, and see what I did exactly. Try to see it. This I solved the same problem going downwards with acceleration A, but now I have chosen the positive direction, choose the positive direction upward. Well, I have chosen, even if A is going downward, I have chosen the A positive, A going up. So if A is going up, the normal is positive, the weight is negative, and A is negative. So if you choose it and you do it, you will find the same result. Okay, so the summary. The summary is when you apply Newton's law, you have to follow the 5 steps. What it said, the second law is the sum of all the forces. You have to sum in a vector form. The sum of all the forces produce acceleration. And what is acceleration? Mass by acceleration, the sum. So the acceleration follow the sum of the forces. If the forces is going to the right, the acceleration is going to the right. But not this one force. It follows to the sum of all the forces. The sum, the vector sum. So once that you predict the acceleration, you know for the chapter 1, 2, and 3 that you can predict the velocity, and you know for chapter 1, 2, and 3 that you can predict the position. So you can predict things. Knowing the force, you can find the acceleration. Knowing the acceleration, you can find the vector velocity. And knowing the vector velocity, you can find the position. In one dimension will be knowing the force, you can know the acceleration, you can know the velocity, and you can know the position x. So it makes you to be able to predict knowing what force is acting on the object.
To finalize, I want you to
Think about this problem. Imagine now that you are in the elevator. The elevator have the guy that is on the elevator is falling down with acceleration. But now I'm going to put an acceleration very, very big. It's falling down with acceleration going downwards of 20 meters per second squared. So it's bigger than the acceleration of gravitational. And the question is, what is the normal force? And where is the guy? Where the guy will end? So the equation that you will say to think about this problem, you will say, okay, there is a weight going downwards. So the weight is going downwards. Let's say that the weight, the mass is 100. So if the mass is 100 and the acceleration is 10, the weight is 1000 going downwards. So this is the weight. Mass by acceleration is 2000 because the mass is 100 and the acceleration is 20 meters per second. So mass by acceleration is 20,000. So the normal cannot go up, have to go down. The normal have to go down in a way that the 1000 plus another 1000 going downwards will be the 2000 MA. The sum of all the forces is MA. MA is 2000. The weight going downwards is 1000. So I need another 1000 going downwards to complete the 2000s. So where is the guy? The guy will be here, will be on the top of the elevator, and the normal force is the normal force that is pulling the guy downwards. This is the normal force, and it will be 1000 newtons. Now, 1000 newtons plus the 1000 of the weight will make MA 2000. If you understand this, you are done. Good luck.